Hello everyone, my name is Nam. I am a research fellow at the International Research Institute of Disaster Science, Tohoku University. So today I will speak on behalf of my colleague, Dr. Keiko Udo and Professor Akira Mano. So my talk is about the assessment of the future flood risk using the projection from a super high resolution global climate model. Okay. So in general, the assessment of future flood risk are usually based on the combination between climate modeling and hydrological hydraulic modeling, so that we can predict or we can project the future risk in terms of stream flows or flow depth at a certain point of catchment. And in terms of climate modeling, so you know that this Earth's surface is divided into a mesh, and the physical processes are modeled for each grid. And I'm sorry. And the distance between the grids are defined as a model resolution. And sorry, okay. And the behavior of the model resolution is similar to the resolution of a television. I think most people prefer HD television to the standard definition television. And the better, the final resolution model, so the better the better diagnosis of our climate system. And this figure shows the timelines of the model resolution improvement since 1990 up to 2001. So we can see that from the beginning, the resolution of the climate model started with 500 kilometers in grid distance. And up to 2001, the grid distance has been increased up to almost 200 kilometers in distance. And as a nature of the extreme phenomena, it is usually occurred associated with a local scale effect. So this kind of climate model with very coarse spatial resolution couldn't capture the extreme phenomena, especially the extreme rainfall. So that the flood risk assessment based on this cost model usually show moderate estimation of the flood risk. As benefiting from the computational power, so in 2001, the climate scientists at the of Japan has proposed a very super high resolution climate model with the grid distance is 20 kilometers. So this model is designed in expectation that it can capture well the behavior of the extreme events. So we can see here the representation of the Earth's surface is very close to the reality. And because of the resource and time consuming, so the super high resolution climate model was just experimented for 3 time slices of 25 years. For the present climate from 1979 up to 2003, and for the near future climate 1915 to 39, and the future climate 75 to 99. And in the context of this presentation, we will focus more on the impact of the climate change on this period, the future period here, where most most extreme phenomena are expected to occur because the greatest increase in the future temperature. And the model was experimented based on the A1B scenario. I mean the emission scenario A1B, which means which considers the balance using between the fossil and non-fossil energy consumption. And this presentation, we apply the super high resolution climate model for one of most flood-prone area located in central Vietnam. So we can see here, this area usually receives greatest rainfall amount as compared to the other places. So here we can see the distribution of the maximum daily rainfall in the for the 25 years in the present date climate. And if we look at the performance of the climate model by comparing the actual observation of the maximum daily rainfall in the field, and that predicted by the climate model, so we can see a very good ability of the model to capture the extreme events here by showing a similar rainfall patterns and the reasonable rainfall intensity. However, as a nature of climate modeling, there are always existing discrepancies. The error between the model and the observed from the field. So we should apply a correction method before using it in practical cases. In this presentation, I am not going into details about the model correction processes. So this I would like to move to the result of the study. So by looking at the projection of the model for the future climate here is the rainfall at a location in elevated area here. So we can see the solid line is the rainfall intensities over a certain period of time as compared to that in the present day climate, the dotted lines here. So we can see the significant increase of the rainfall intensities and the frequency in the future, because we can see here the 10 years recurrent rainfall intensity will probably exceed that those with 25 years recurrence in the present day climate. However, in the low-lying areas, we can see that there is a very little change, actually very little change in the rainfall intensities in the future climate. So doing the same, so we can plot out the spatial increasing in the future precipitation. So you can see in the elevated areas, the more increase in the precipitation are expected. So for the assessment of the future flood risk, so we have already projected the future rainfall, and then we use it as an input for the hydraulic modeling, and so that we can predict the water state and inundation depth in the flood plain area. So this figure showing you the comparison between the present day flood and the future flood. So we did here we presented here the most serious flood in the present day climate, and we compare with the future here. If we overlapping these two figures together, so we can see here the increased portion of the future inundation area as compared to the present day climate. So we expected that about 50% of the future inundation area will increase in the future climate, and mostly focus on the downstream of the river basin. And this part, this is a flat plane here. And if we look further into this portion, so this is showing you the flooded area caused by the 1999 flood, the most serious flood in the past. And we can see that only the riparian, the riverine area were flooded. But in the future, this flood, this inundation extent will further extended inside inland. So we can see here, and the point here, this is very dense people. So we should think how to propose a proper flood mitigation and mitigation measures. By comparing, this figure shows the comparison in terms of flood height, inundation height. So this figure showing you the inundation height somewhere over here, about 5 meters in the present climate, and it will increase up to 7 meters in the future climate. So that at the moment here is the present structure for in the downstream of the river basin, and in the future, these areas actually these heights it could be is projected to be inundated. So what should we prepare? And you know that throughout the country we have 1,000 of reservoirs. At the moment, the reservoirs can have enough capacity to capture, to regulate the flood by using the capacity here. But in the future, when the precipitation is increasing, this capacity might not be insufficient. So we propose a new future policy that we should release the reservoir storage in advance before the storms coming, so that we have more capacity for flood control here. So in these figures, so we can see here is a current policy. So we can see here the inflow and outflow. So if we can see here the maximum flood reduction here, and by using the advanced release, so we can reduce the outflow peak, the outflow peak to downstream. So we increase the margin of the flood reduction. And by using a short-term prediction model, so we can reduce, we can show here the reduction measure is here's a coefficient about 40% reduced as compared to the present policy. And I have some remarks here. So this assessment of the future flood risk apparently neglected the effect of the non-climate variability like land use and urbanization process. And it also neglected the uncertainties because of the constraining in defining the emission scenarios. So that is the end of my presentation. Thank you very much for your kind attention.